with those, here's going to be rectangle number 1, rectangle number 2, 3, and then 4. But with all the different types of rectangles, we just want to make sure we're using the correct one. So for this first rectangle, if I want this to be circumscribed, if I go up from the left, this would be a little more familiar to us if we had done these back to back, but now we had a break. We wouldn't want to do that because that would have been inscribed. So we don't want to go up and use a left endpoint rectangle. But if we go up from the right, touch the curve, and then cover that base by going to the left, that gives us a rectangle and it would be considered circumscribed. So that's our process. If we follow that same pattern, up from the right, move left, then we should end up with our 4 rectangles, and they should all be circumscribed rectangles. And then if you recall, to figure out what our change in x was, we did the difference in the interval. So 3 minus a 1 divided by the number of rectangles that I wanted. So that was 1/2. We then labeled that on our graph. So we started at 1, we move over 1/2 to 3 halves, another 1/2 is 2, and then 5 halves, and then our 3. The ones that we are concerned about, so I'll make bigger red dots on this, are the 4 places that we touch the curve, because those 4 places are where we're going to be able to determine the height of our 4 different rectangles. And remember how we called these, they were kind of weird, but we called these C sub 1s. So our first C value is just the first x coordinate where we touch the curve, so that's 3 halves. And then we would have used 2, and then we would have used 5 halves, and then we would have hit the curve at 4. And again, I'm just getting these from the 4 places where we touched the curve. So then using these, what we then set up is what we called a Riemann sum. So that was the whole sigma notation. We reviewed sigma notation on Friday at the beginning of the class. We put a 4 at the top because that's the number of rectangles that I'm going to be adding. Our lower limit would have been a 1. We're always going to start at 1 with these. And then we wrote our own general term, and all of our general term really was just our height times our base. Our base for this problem is this 1/2. So every rectangle has a base of 1/2. The height of all of these is where this was somewhat weird. It's really just our function. But remember how we talked about we don't want to call that f of x. We wanted to call that f of c sub k. So we didn't want to just write x squared plus 2. Because the way the Riemann sum works, I should be plugging in a k value of 1, 2, 3, and then since my upper limit is a 4, that's what should be plugging in, and those aren't the numbers we want to be plugging in. We want to be plugging in these numbers over there. So the way we wrote that instead of x squared, we wrote that as c sub k squared. That way when I take a k value of 1, then I would get c sub 1 squared, which is really just the 3 halves. So it really is just us taking these x values over here. The notation is somewhat important. The important thing is it's these values here that we're now plugging in. So if I now go and find the area of rectangle number 1, it should be this x value here, the 3 halves squared, plus 2, multiplied by the base of 1/2. If we did that individually, that's the area of rectangle number 1 right here. If we go to the second one, that is 2 squared plus 2 times 1/2. That would give us the area of rectangle number 2 in our graph. And then we just continue on with those next few. So 5 halves squared plus 2 times 1/2. And then the last one, 3 squared plus 2 times our 1/2. These are the 1, 2, 3, 4 individual areas. Then it's up to you. I'm going to give these to you because typically I have people plug these in. There is some, precision that you need with this. People make mistakes plugging all these in. We don't necessarily have the time to take and have you guys plug all those in. But when we plug that in, it should give you 14.75. So now compare that to the previous one. Remember how we got 10.75? We would have said this would have under approximated because we were losing area. We didn't accumulate all the area underneath the curve. But if we look at this one is over approximating So this is a little bit bigger. So now we know we're somewhere between 10 and 3/4 and 14 and 3/4. The area's got to be somewhere in between. Okay. All right, and then the last one of these, and then we'll finally get a different looking shape. Same exact thing, but now we're going to do the midpoint rectangles. So we can shorten this up a little bit. So go 1 to 3. I still wanted all the same information, so we're going to do it with 4 rectangles, so we can still cut these in half. We're still going 3 to 1, so we're still going to move over by halves each time. But now the midpoint rectangle means if I look at this first base, so between a 1 and a 3/2, I want to go up from the middle, touch that curve, and then half of the rectangle goes outside to the 1, half of it remains inside as we go to the 3/2. The same for the second one, between 3/2 and 2, I'm going to go left and right. And we just continue that pattern, hitting it in the middle each time. So the initial setup is the same. If I do my whole sigma sign, I'm going to start at k equals 1. I still want 4 rectangles. I'm still multiplying my height and my base. All the bases are still a length of 1/2. My height is still that parabola, x squared plus 2. Then I'm just going to write as c sub k squared plus 2. So nothing is different here. The only thing that changes now when we start using different types of rectangles are the x coordinates that I'm now going to use to figure out the height of all of these. So what we now have to do, the reason this takes a little bit more work, although these are hopefully good numbers for us to work with, this first c value right here should be the number that's directly in the middle of 1 and 1.5. All right, so between 1 and 1.5 here should be 1.25. So I'd write it as 5/4. The number in the middle right here between 1.5 and 2 would be 1/75, so 7/4. And then our number in the middle here is 9/4. And then this final midpoint would have been hitting the curve at 11/4. So these are the midpoints where we're touching our curve. So that is what we want to be using to figure out the height of all of these. Any questions on the understanding this? All right, I'm not gonna, if you wanted to write all these out, number 1, number 2, number 3, it's the exact same thing we would have done right here, except these numbers that you're plugging in for x are no longer 3/2, 2, 5/2, and 4. It's 5/4, 7/4, 9/4, and 11/4. And you're just plugging them in, you're gonna add them all up. If we go and plug these in at some point, you should have an idea if this was under approximating, this was over approximating. We should have an idea of where this number would fall, because the midpoints, while you're going to gain some extra area here, you're not accumulating everything. So we go outside the curve and we lose some inside. So you're kind of giving and taking at the same time. So this should be in between those two. All right, so when you plug these in, it should be sort of right in the middle. It's not necessarily in the middle, so don't necessarily write that. But what we would get here, at some point you may want to do this just to make sure. That's what you would get if you did the midpoint method, 12.625. At some point, definitely take a minute or two and do those. Or if you do that optional worksheet, make sure you can plug these all in correctly and get those answers. Then we get to 4. Which one of these would most accurately approximate the area? One of them should be, we've already talked about it. It's definitely these midpoints. To prove that, let me now actually show you what this area was. So if I now graph this, so x squared plus 2, we'll change our window. We'll just go 0 to 4. Let me make the window a little bigger for the y's also. And then we'll show what the real area is, but it should be pretty darn close to that 12.625. All right, so window. So we'll keep it at 10. All right, so there's our parabola. And then now you'll know what this means in a minute. But if I go down to number 7, one more, see the little weird S-shaped thing in front of that? If we have time today, we're actually going to get to that. But if I now enter this, and I want to figure out what's my lower limit, I told you to go from 1 up until 3. So that's my upper limit. And notice how it's going to shade that in for us. And then it gives us this area. So the exact area underneath that curve is 12.666 repeating, 12 and 2/3. So if you look at your midpoint approximation, that's pretty darn close. We got 12.625. The midpoint rectangles are incredibly accurate in terms of giving us the real area underneath that curve. All right. All right. So with that, we can finally look at a different looking shape. So go to number 5. Do not, because here's what tends to happen with people. Everybody just immediately draws in a parabola on the right-hand side that looks like this. So that's just because I like doing a bunch of them that look the same, so we understand the difference. When we draw this in, draw the correct parabola. So in this case, this is 4 minus x squared. So this is now a parabola with a vertex up here at 4, and it opens downwards. And its x-intercepts should be at 2 and -2. And I want you to go from a -1 to 1. So we want to approximate the area in here. Still want you to use 4 rectangles, so that's still going to allow us to cut that in half and then cut each of those in halves. And if we do that, then we should have our 4 rectangles. To figure out what each of those is, our change in x is always the difference in the interval. So 1 minus a -1 divided by the number of rectangles. So we're still going to be moving by 1/2 right now. So if I start at a -1 and I move over a half, that takes me to a -1/2. And then 0, positive halves, and then 1. What I want you to do real quick, because this is really, there's 2 ways people mess this up. They plug it into the calculator wrong, or they pick the correct or incorrect values where we're going to touch the curve. So draw those 4 rectangles in. And the important part is, where do we want those rectangles to hit the curve so that they are inscribed rectangles? So try to draw those in, and when you draw those in, then identify the 4 x coordinates, so the c values, where we're touching the curve. And your main priority is making sure that they are always inscribed. So every rectangle must stay within the curve. All right, let's see what we use. So if I do this first rectangle, was the x value of a -1 the first value that we would want to use here? Did that produce an inscribed rectangle? Yes. So if I go up from the -1, touch that curve, and then cover this distance that I'm supposed to cover, I get a rectangle and it's inscribed. So currently I did left to right. So if I go up again from the left side, touch this curve, and move to the right to cover the second interval that I needed to cover, was a -1/2 another number we would use? Yes, because that produces an inscribed rectangle. So if I continue to go up from the left and I touch the curve and then now come to the right to cover the next interval to get to the 1/2, did 0 work? No. All right, so this is one where you have to kind of sketch these in and make sure that we're doing them correctly. The 0 actually produces a circumscribed rectangle. So to cover this interval from 0 to 1/2, we had to switch, go up from the right and move left to cover that. So we skipped the 0 and the 1/2 should have been your next number. And if we now continue that pattern going up from the right and moving left, then we're good again. So those would have been the 4 numbers that we would use. From there, we can then set up our Riemann sum. So we're going to do k equals 1. We wanted 4 rectangles. All we're doing again is finding the areas of rectangles. So this general term should be our height times our base. Our base for this one is still 1/2. We found that right away. The height is your function, the 4 minus x squared. We're just writing it as 4 minus c sub k squared. And then times that 1/2. We then take these numbers and plug them in and evaluate. Yeah, Carter.
Why would k be equal to 1? Would it be -1 or is it just 1?
So it's not this one. You don't want to think of it as this one right here. It's just when we do our Riemann's, our sigma sums from the other day, this lower limit can start anywhere we want. We always want to start at 1 for the ease of things. These k's are, we have to plug in 1, 2, 3, and then since our upper limit is a 4, we have to plug these 4 integers in for that general term. We have to. So 1, 2, and 3, since it's 1 to 3, we have to plug these in only. So our k is a 1. That's why what we're ultimately doing when we write our general term, we're making the subscript the k, because we have to plug in the k value of 1, and then 2, 3, and 4, and we're just making that our subscript so that we actually now get the first x coordinate, the second x coordinate, the third, and then the fourth. All right, does that make sense? Okay. Okay, last one real quick. Well, sort of the last one of these. Real quick, sketch, did I give you that answer? Did I even give you that yet? No. That should give us, so at some point, if you sit down, plug these in, make sure you can get through them all, should give you 6.75. That's a little bit of an under approximation. We're losing these areas here. So we know our area is a little bit bigger than 6 3/4. All right, number 6. Same thing, sketching that same curve, still have a -1 to 1. I still want you to use 4, so you're going to split that up. None of those details from above changed. So all this is the same. So we have our 4 rectangles ready. The only thing I now change is draw those in so they're circumscribed. So same idea, draw them all in, and then list out the 4 places where we're going to hit the curve to make sure they're all circumscribed. Okay, this time we know the -1 shouldn't work right away because we just did that and it produces an inscribe. So we should definitely not be considering that one. And we would hopefully know we've got to go up now from the right, hit the curve, cover that first interval by going from right to left. So the -1/2 would have worked. If I follow that pattern and again go up from the right, move left, we're good there. So we would use that 0 as the next one. But then the opposite of what happened in the last one, although similar, I guess. We can't continue that pattern because if I continue to go right from left, I'm going to get an inscribed rectangle. So just like the one before, we then got to kind of switch the pattern we were doing. You're going to go up from 0 again, hit the curve, move to the right. And for the third one, you're using the 0 again. And then from 3, left to right, or for the last one, you go up from left to right, and then now that 1/2 would get used. Before I tell you the answer, we should hopefully understand that the answer I'm about to write down should be bigger than the previous one, because where that one was an under approximation, circumscribed in this case is going to be an over approximation, so this answer should now be bigger. And in this case, it is 7.75. Right, when you plug all those in. Again, just keep in mind, you have to do this on the quiz, so please make sure at some point we can actually take all those in, plug them in, and get those answers. All right. Now, here's where this really gets used, because clearly you now know there is a way on the calculator where we can get the exact area. So it becomes kind of a moot point once we learn how to do this on the calculator, or even without the calculator, there's a way we can get the real area. Where this is really valuable and where we really need this is, let's say we just have a table of data and we don't know what this curve now looks like in between. So the tables are really where these are going to get used all the time. So it says the table below gives values of some function, which is nice because we don't have to figure them out. And then it says, using the table, approximate the area underneath the curve f of x. We don't know what the function is, with 3 left endpoint rectangles. So this has to start the same. We want to know what is the length of each base. And the way we find the length of each base is by calculating that change in x. So we want the difference in the interval. So we're starting at 0, we're finishing at 12. So I have to cover an interval of 12, so 12 minus 0. We want to do it with 3 rectangles. So that means we need to have a change in x of 4 to start at 0, finish at 12, and end up with our 3 rectangles. Strongly recommend actually drawing these in. So if we had drawn them in like we did above in the previous 3 problems, we would have gone up from 0 and we would have moved over to 4. This would be rectangle number 1. Then I have to go over another 4. So now I'm going to go over from 4 to 8. That would have given me my second rectangle. And then from 8 to 12, I would have gotten my third rectangle. The types of rectangles that I then wanted you to use were left endpoint rectangles. They kind of overlap there. So if you look at rectangle number 1, its left endpoint would have been right here. If we had the graph drawn, that's where you would have put your big dot. That would have been the x coordinate that we would have used. For rectangle number 2, its left endpoint would have been right here. And for rectangle number 3, its left endpoint would have been right there. The nice thing about the tables, they give us all this data. So we are now ready to write our Riemann sum. We're not as worried about all of this here. All we are now saying we're doing is we're multiplying together our functional values and our change in x. You don't have to worry about c sub k's, you don't have to worry about any of that weird stuff. So for rectangle number 1, all I need for rectangle number 1 is its height multiplied by its base. The base is easy. We've already found it. Every base is 4. And the height of rectangle number 1 is always the functional value. Like, what is the height of the curve? So for rectangle number 1, wouldn't our functional value have to be this 4 right here? So we're going to have a 4 times a 4. For rectangle number 2, its height times its base must be 4. The functional value at the left endpoint is 3. So this is a 3 times a 12. Plus rectangle number 3, height times base. Its base is 4. And then the functional value at the left endpoint has to be 10. So the nice thing is tables is where we use this a lot, and tables are the easiest ones. It's quick, it's simple. So we should have 16, 12, and 40. So what is that? 68. All right. Okay, and then 8's the big one. That's why I like kind of concluding this set of notes with this problem, because it ties in basically what we now do in this whole next B portion of the course. We use fancier words now instead of X's and F's. It says oil is leaking out of an oil tanker damaged at sea. The chart below provides the information regarding the leakage of oil in gallons per hour. So now look at this unit here. Let me not even do the leakage word. Gallons per hour during a 4-hour period. Then it says using 4 left endpoints, approximate how much oil has escaped. So now let's go back to something we've talked about in the past. If you look at the unit that I gave you, gallons per hour, and we talk about what does that give us, a position unit, a velocity unit, or an acceleration unit, hopefully we would all understand that gallons per hour is a velocity unit, gallons per hour, position over time or amount over time. When we answer this question, and I am asking you how much oil has escaped, if we're looking for the amount of oil that has escaped, would we all agree that the unit would have to be a unit of simply gallons? Well, now think about what unit that would apply to. Is gallons a position unit, a velocity unit, or an acceleration unit? Wouldn't that have to be a position unit? So what this is now doing, this is taking us from a velocity, and it's actually now moving us up the chain that we've been going down all year. If I've had a position, the derivative is velocity. The derivative of velocity is acceleration. We're always going down the chain. Somehow by finding the area, it actually brings us upwards, and it allows us now to go from a velocity up to a position. All right, and that's sort of what we're now getting into over the next 3 chapters, okay? So as we now do this, we still want to kind of go through those same processes. We want to figure out what's our base first, and that's our change in X. So in this case, we're going to do 4 hours, so 4 minus a 0, the difference in the interval covered. I want 4 left endpoint rectangles, so my unit of time is going to be 1 hour. I would draw these in, so if I'm going to start at 0 hours, I'm going to move over 1 hour to get rectangle number 1, another hour to get rectangle number 2, another hour for 3, and then another hour for my 4th. I kind of covered it up with my marker, but you see here 4 left endpoint rectangles. So again, left endpoint. So we're going to put our dots on the left endpoints of those 4 rectangles. And again, the nice thing about this is we can pretty much just go right to getting these answers. What we are now finding the sum of, think about your units and why this is now going to work. What we are going to be multiplying together, our functional values now have units of gallons per hour. And we are now multiplying those by a base, which has a unit of hours. So each product that we are about to produce is a gallons per hour multiplied by an hour. So that product should be yielding the final unit that we know we should be getting, which is gallons. Okay, I think I'm going to run out of room, so let me erase this real quick. All right, so same thing. Number 1, again, the tables are nice. They give us all this information. We know our height, or our base is 1, and our functional value at the left endpoint should be 50. And again, that's 50 gallons per hour for 1 hour. So that's 50 gallons. For rectangle number 2, its left endpoint functional value is 70 gallons per hour multiplied by the base of 1 hour. So now that's 70 gallons. And just continue on. 97 times 1 for the 3rd one. And then the 4th one is 136. It's not a 6. 136 times 1. All right. Add all those up. Those are giving us our unit of gallons. And that should give us 353. And then the unit that now produces is gallons. So if you've been in physics, you've done the idea of area, and somehow that area is producing, like allowing us to kind of go up that chain. It's the same effect that we're doing here when we're doing these algebraically, okay, when we're not just looking at a graph in the area underneath the graph, okay? All right, Good with all that? All right, then I really don't have time to waste. So we are going to, if you have that packet, you're set. Just go to the next one. And we're going to cheat a little bit with this to make sure we get through as much as we possibly can. If Cami will open and cooperate with me. Not a problem. But go to 5.2 day 2. All right, there we go. You can see my circle of death up here. Hopefully it'll. Come on. All right. So I'm going to have you fill in this table. We're going to do, we usually go through these pretty thoroughly. We're not going to go through them quite as thoroughly as we normally would. I do want you to sketch this curve though, so we at least know what it looks like. So take this function, we'll do it up here. That's the parabola with the vertex up here at 8, and then it opens downwards. And then I want you to go from 0 to 4. 4 just so happens to be our y-intercept or x-intercept, so that's nice. So we're approximating that area in there. And I want you to use initially 4 rectangles. And again, we're keeping this pretty straightforward. So if I'm going to do 4 rectangles, my base should be the change in x. Our interval is 4 minus 0. I want 4 rectangles, so we're going to be moving over by 1 each time. Again, we're not going to be quite as thorough. Go ahead and say k equals a 1 in our sigma sign, and then I want 4 rectangles. We know that our function is 8 minus 0.25, and then we call this c sub k squared. And then my base in this case is 1. If I did 4 rectangles to cover 4 units, my base is going to be 1. All right. So when I have 4 rectangles, if we actually went through all the work, and we've done plenty of them today, your answer should be 24.5. Now, all I want you to figure out in number 6, if I ask you what is your base in number 6, if we had to do this problem, I would now have to do again 4 minus 0. But now I'm going to split that up for 6 rectangles. Notice how your base would now become 2/3. So my base got a little bit smaller. If you go to the 8 rectangle one, we're going to do 4 minus 0. And I want to split this now with 8 rectangles. Now my bases are going to be 1/2. They're getting smaller and smaller the more rectangles that I jam in. All right, so now this is going to really help us to speed this up, I hope, if it works and doesn't take forever to pop up. All right, so this is this problem. If it doesn't freeze on me, which it's doing.